Test. People online hear me? Thank you. All right, good morning. Let's get started. So another week of grinding here. So let's continue on the second order ODE. So just a very quick review. So we started. This is the general format of a second order ODE. And we said we're going to deal with linear second order ODE. So this is basically a linear format. First, what we're going to look at is homogeneous one, which means when f of t equal to 0. So let's look at the homogeneous, how to solve a homogeneous linear second order ODE. And then the general concept is solution means we want to get a general solution. So I touched upon the general solution. As you can see, basically a formal wording of a general solution would be, it's a family of solutions that contains every possible solution of this differential equation of the ODE. That's why it's called a general, right? So it's not a particular, which brings us to the concept of particular solution. So when you see particular solution, it basically it's just one member of this family of the solutions. Okay. So the question is basically, how do we obtain this general solution? In order to reach to that point of how general solution is obtained, I need to present you with a number, maybe 3 theorems, okay, in order to formally derive the so-called general solutions. So let me present you with 3 theorems. Let's take a look at the first theorem. First one says, if y1, so let's say y1 of t, if this is a solution, okay, to the equation, let's call this equation 1, okay, so that's the homogeneous linear second order ODE. Suppose you have a solution, which is y1. And y2 is another solution. To equation 1. So basically, you got 2 solutions. Okay, so I don't care what a relationship yet. Okay? Just assume you got 2 solutions. Then C1 times Y1 plus C2 times Y2. So basically, you multiply Y1 and Y2 with 2 constant, C1 and C2. So this is also a solution to equation 1. That's theory number 2. C1 and C2 are constants. And this theory actually is a direct result of the linear system property. We call the linear system property, there's a superposition property, right? So when you have a input of y1, there's input x1 and x2, then you have an output. If you change the input and using the superposition rule, you also have the output, right? Yeah. So this is actually a direct result of that. So I'm not going to provide a proof right here. You can take a look at the lecture notes for the proof. It's actually quite straightforward. So that's theorem number one. Okay, so just remember, you can create a different solution based on a combination of two known solutions, y1 and y2. Okay, so that's basically what theorem number one is. And you can create essentially infinite number of other solutions, right? As long as you have a y1 and a y2 are two solutions. That's first theorem. Second theorem, this is kind of related to what you probably learned in linear algebra. Okay. So here's the formal description of the second theorem. Let's consider a set of functions y1, y2, up to yn. So there are n number of functions. We call them y1 to yn. Then so what we're going to call them, then we'll say these functions. Okay. We also say these functions they are so-called linear dependent. They're linear dependent. Let's use LD as a short name for linear dependent. So this function is y1, y2 to up to yn. Okay, they're linear dependent if and only if for some k1, k2 up to kn integers, which belong to a real set. So this is basically they're real numbers. Right? So k1 to kn belong to real numbers, not all zero. Okay? So if only if for some of these numbers, maybe n of them belong to a real set, real numbers, and not all of them are zero, and such that the following expression is satisfied, such that k1 times y1, k2 times y2, up to kn times yn equal to 0. So that's essentially theorem number 2. So let's read it again. See if we get the meanings behind here. So you got n number of functions. And then we're creating an expression. The expression is to multiply each one of the function with an integer number k1, k2, and kn, and then you add them together, okay, and let it equal to 0. Right. So now the theorem 2 says you want this whole expression to be 0, right? And there might be in a situation that not all of them is 0, because if k1 equal to k2 equal to kn equal to 0, this expression is naturally equal to 0, right? But there is a situation is that not all of them is 0. Some of them are not 0. And this expression is still can be 0. Right? So basically that's what the theorem 2 says. If that situation is true, then we call these functions linear dependent. That's basically what this one says. I'll give you some examples how to interpret this thing said here. Now, of course, there's another situation, as I just said. There's another situation is to make this expression be 0, okay, to make it equal to 0. If the only option you have is to give this k1, k2, kn to be 0, then That's instead of a linear dependent, then we have a different name. We'll call the linear independent. Right? So that's the sort of extension of the theorem number 2. We said is if only when all the k's, okay, all the ki's, k1, k2, kn, so I equal to 1, 2, up to n. If only when all of the k's are 0, and this equation, let's call this equation 2. If the equation 2 is true. So if that's the only condition to make equation 2 is true, then the set of functions, okay, so that set of functions are linear independent. And we call it Li. So these are two situations. When you have a set of functions, they're either linear dependent or linear independent. And how do we decide the relationship is to use this theorem number 2. So you can construct this equation number 2 here and examine, are you going to be able to get some numbers for the k1, k2, kn, so that the whole thing equals 0, but not all of the k's are 0. Okay. If that's true, then you got the linear dependent. Otherwise, then you got a linear independent relationship. So let me show you a few examples here. As a matter of fact, if you drop your mind, I mean, when you have a set of equations, and when you want to solve that set of equations, the first step you do is you put all the coefficients into a matrix, right? N by N matrix. Okay. And you have learned in linear algebra, the only situation that you can have a unique solution when you have an N by N matrix, okay, is that the N number of rows has to be so-called linear independent, right? That's the linear algebra solution knowledge you learned, right? Okay, so let's look at give you a couple examples here and to show you what linear dependent or linear independent really means. So let's say I have a y1 equal to t squared, y2 equal to 2t squared. So this is very simple. So basically you have a set of functions. I only have 2 functions set here. And the question is are the 2 functions Li or Ld? So linear independent or linear dependent? Okay, yeah. So take a wild guess. Do you think you're linear dependent or linear independent? These 2 functions. So independent. Okay, so maybe before we formally prove this, let's think about the wording. What does dependent and independent means? Excellent, right? One relies on something. Okay, maybe thinking in terms of family relationship. When you fill out the form, and as a parent, sometimes you fill out the form. Do you have any dependents? Okay, so that's the word independence, right? So if you have some kids, of course, not you. I mean, if I have some kids, then the kids must come from a couple, right? So there's from me and from my wife, and then you have your kids. So technically, your kids can be written as a function of the mom and the dad, right? That's why it's called dependent, right? Otherwise, it's not independent, right? So you and I are not related, so you're not my dependent, but the kids are related to me, so they're dependent. That's basically what dependent means, or independent means, right? So if you look at the two functions that are here, they're asking, are the two functions dependent or independent? So if you can also think in terms of that perspective, right? You can see, okay, this is t squared, this is 2t squared. Look at that. They're like a brother sisters, right? So they must be dependent of each other, okay? But of course, we want to formally prove this, so we can use the theorem number 2 at here to formally prove that. So we can see, okay, let's say k1 times t squared and k2 times 2t squared, and let it equal to 0. So you create this expression and you let it equal to 0. Then for this expression here, right, you get, you literally, you can cancel the t squared. So you basically, you get k1 plus 2k2 equal to 0. And when you reach at this stage at here, you have one equation and you have two variables. So technically, you can find infinite number of solutions for k1 and k2, right? So one of the solutions, you can even create a solution, say, okay, for example, I can get a solution that k1 equal to -2, k2 equal to 1, and that's one possible solution, right? And then for this solution, you go back to the theorem. Obviously, they're not 0, and actually not all of them are 0, right? So you basically, you find some values for k1 and k2 which are not 0, and you're able to make this k1 times y1 plus k2 times y2 equal to 0. So that's exactly the condition for linear dependent according to theorem 1. So that's why you can see the two functions are linear dependent. Yeah. And if I have to use, let's say, some analogies, for example, maybe another set of functions, let's say t squared, 2t squared, 3t squared. Okay, so now I've got 3 functions. And obviously, you will conclude that this is linear dependent, just like the two set functions like here. You know, if I use an analogy, for example, let's say these two, if these two are the parents, and this is the kid. So then you can clearly write down the kid, which is 2t squared. And so the kid comes from the parents. How would you be able to generate that kid from the parents? So you can see, okay, that 3t squared minus the t squared, right? Okay, so with this genetic operation, and you create this 2t squared. That's called dependent, right? So this is clearly linear dependent set of functions using that kind of concept. Okay, good. So let's take a look at one more example. So let's say I have a set of functions. One is cosine x, one is sine x. Are these two functions linear dependent or linear independent? Okay, this might not be as straightforward as the other example, but you can certainly use the same approach. So we set up this equation and let this equation, right, let the expression to be 0. And then let's examine, are we able to find certain value for k1 and k2, which are not 0, to make this expression equal to 0? Or are we not? Right, that's basically the question. So what do you think? Do you think you can find some non-zero values for k1, k2, so that non-zero, so that this whole expression equal to 0? Nodding means yes. You can. Can you give me an example? What would be a value of a k1, k2 so that this whole term is equal to 0. No, K1, K2 has to be numbers, not functions. Right? So that's actually a good point. K1, K2, remember the theorem says K1, K2 belong to a real set. So they're not functions, right? They're numbers. And they're essentially it's a nonlinear function. So you actually won't be able to find any non-zero K1, K2s to make this expression equal to 0, right? So the only way to make this expression to be 0 is to let the two numbers equal to 0. That's the only way. So according to theorem number 2, then the two functions must be linear independent. This is actually a good result to memorize. Okay, when you have a two sine function, sinusoidal functions, okay, they are actually sine x, cosine x, they are linear independent. Good, yeah. Let's see one more set of function here. So x, x squared, x cubed. For these three functions, are they linear independent or linear independent? What did I say? Linear dependent or linear independent? Again, it may not be as straightforward, so you should create a set of this expression at here. Okay, yeah. So you look at this polynomial at here and let it go to 0. And K1, K2, K3 are the coefficients of the polynomial. Okay. So this is another situation. If you want to make this expression equal to 0, and K1, K2, K3 has to be numbers, okay, not variables, your only solution is K1 equal to K2 equal to K3 equal to 0. Okay. It's very much like a you got a 0 times x coefficient here, right? And that's basically the only way to make this whole thing equal to 0. Okay, so let me show you one more example. X squared, 5x, and 2x. Okay. So let's use the expression K1 times x squared plus K2 times 5x plus K3 times 2x equal to 0. Okay. And then you can combine the common terms. So here's x, that's a common factor. You get 5k2 plus 2k3 times x equal to 0. And then you're trying to make this expression to be 0. And we want to find whether there's any situations that can exist that the non-zero case to make this expression to be 0. So what do? We can set the coefficients, okay, for x squared to be 0 and set the coefficient for x to be 0. Okay. And that, see if we can get some solutions, right, after this setting of the two coefficients to be 0. And the first one already give you K1 equal to 0. And then the second one has nothing to do with K1. The second one is just 5K2 plus 2K3 equal to 0. So you have two variables here, and then one equation. And again, you can have infinite number of options, solutions for K2 and K3. Right? So there can be a solution, for example, K2 equal to, for example, 1. And then K3 -5/2, for example. So bottom line is the second one here will give you some non-zero values for K2 and K3. So overall, when you look at the K1, K2, K3, there exist non-zero values, right, among the Ks. Then according to theorem number 2, so there's some non-zeros, not all zeros. Then that set of functions must be linear dependent. So then you can make a conclusion. They are linear dependent. Okay. Yeah, the trick here is x squared. To be honest, x squared is not quite related to 5x2x, but then 5x2x are related at here, right? They're similar to each other. So, but when you put them together, then you can see, you can still force them to see they are all related. You know, they're linear dependent. Okay, and that's the point. So you look at the way to test linear dependent or linear independent. The first step is to create that expression. And then the second step is see if you can simplify it. Okay, group the similar terms, and then you make the coefficient to be 0 and try to solve for all the Ks. Say you can get a solution of the case, maybe one of them is not 0. Okay, if you can show that, then you can make a conclusion that they're linear dependent. Otherwise, they're linear independent. Okay, now in the future, okay, when we learn next, there's a concept called to create a matrix. The matrix name is called Wronskian. Okay. So we can use that approach also to show whether a set of functions are linear dependent or linear independent. Okay, so just keep in mind. We will come back to this as to what is the Wronskian here. So Wronskian is essentially it's going to be a matrix. It's created based on the set of functions y1 to yn. This is a matrix. And that will be a much more formal algebraic way to prove whether a set of functions is linear independent or linear dependent. Good. So this is a theorem number 2. Okay. Yeah. So we will make use of the theorem number 2 at here in order to create a general solution. So just heads up, if you need a general solution and you need to have 2 linear independent particular solution first, which actually brings us to theorem number 3. How a general solution can be constructed. So this is the actual theorem for finding a general solution for this homogeneous second order ODE. Here's what theorem number 3 says. If y1 of t and y2 of t are 2 linear independent functions. That's a assumption, right? Or fact that you assume linear independent. And they're also particular solutions. So there are also particular solution to this equation. Okay. So let's call this as equation 3. Technically, we listed that equation as number 1, right? Okay, so they're linear independent. They're also particular solutions to equation 3. Then the general solution is given by the following expression, given by y of t equal to c1 y1 of t c2 y2 of t. And that's basically what theorem number 3 says here. So this is the general solution. C1, C2 again, they're constants. Yeah. So now you can think in your head, right, the 3 theorems here. And the first theorem says if y1, y2 are 2 solutions of that homogeneous linear ODE, then C1, y1 plus C2, y2 is also a solution. Right? It didn't really say anything about general solution. Okay? Then the second one is a theorem is to determine how our 2 functions can be linear independent. Right? Then the third theorem is giving a second order ODE, homogeneous one, and if you already have 2 particular solutions and they are 2 linear independent functions, then you can create the general solution by multiplying C1 with Y1 plus C2 with Y2. So that's sort of the flow of the logic right here. This Y1 and Y2, these 2 solutions and these 2 linear independent solutions, we sometimes call them the bases. So they're the bases that you use to create this general solution. Right? So I think the 3 theorems has given us a very general guidelines. Right? So now you can clearly think, if I want to get a general solution for this homogeneous second order E, then the objective is to what? Is to obtain 2 linear independent particular solutions. And that will be the objective. So objective is to obtain a 2 Li solution. Not just 2 solutions, they have to be linear independent solutions. Okay, all right. So now let's look at a general approach to get a solution. So first, I'm going to consider an easy case. So let's consider a second order homogeneous linear ODE with constant coefficients. So this is a second order, a linear second order ODE with constant coefficients. So A and B here are two constant numbers. And then let's see, what is the solution for this type of ODE? Okay. Now, to jog your mind, let's recall the first order one. I'm writing down here's a first order linear ODE, and it's also a constant coefficient at here, the A at here. Okay. And you can solve this one quite easily. And you can solve this using separating variable. Okay. So you get y equal to c e to the power of at. So the solution to this first order ODE is this. And that's the general solution. If you have an initial condition, you can put it in, you get a value for the c. So basically the solution to this, okay, as you can observe, it has an exponential function in it. So that's a first order one. So the question here is, okay, would there be any maybe similarities? So if a first order's constant coefficient with constant coefficients give you a solution that contains an exponential function, then is it possible that the second order linear ODE with constant coefficient also has some sort of exponential function in its solution, right? So that's basically the idea here. How do we start? By finding the solution. So the idea is it possible? So let's call this is equation number 4. That the solution to equation 4 contains exponential function. So with that question, and let's explore the idea. Well, I guess if we want to explore this idea, so let's let y equal to e to the power of lambda t. So let's try this out, right? See if it works or not. So basically, the point here is there a value for the lambda? Lambda is a certain constant. Is there a value for the lambda so that the e to the power lambda t is actually a solution to this equation 4? Right? And we want to show that if possible or not. So basically, you are trying to see if e to the power lambda t, if a lambda exists such that e to the power lambda t is a solution. Okay. Here's the logic. Okay. So we don't know that, right? So we had to find it out. And to find out, then the only way to find out is to plug in this e to the power lambda t into this equation number 4. Right? When you see something in a solution to an equation, what does that mean? Basically, you plug in that into that equation and see if that function satisfies this equation or not. Right? Very much like if you have a function f of x equal to 0, and you see x equal to 1 is a solution, how would you verify? You plug in x equal to 1 back into the function, right? See if the x equal to 1 satisfies. So we need to plug this back into equation 4. And to plug this back to equation 4, as you can see, equation 4 involves y, so that's good. So we're going to plug y right here. And it also has y prime and y double prime. So what I need to do, so I need to calculate the y prime and y double prime first, okay? And then we do the substitution. So y prime equal to the derivative of this exponential function So e to the power lambda t times lambda. And y double prime, right, is to take another derivative of the result, okay, or the derivative y prime, then you get lambda squared, okay, e to the power lambda t. So that's lambda, that's y prime, y double prime, and you also have the y at here. So now I'm going to substitute the three things at here back into equation 4. Equation 4 is right here. So what do I get? I get lambda double prime lambda square e to the power lambda t. This is y double prime. Then a times y prime. Okay, it's the second term. And the last term is y. It's b times y. So b times e to the power lambda t. And equal to 0. And what's nice is you have e to the power lambda t, okay, everywhere, okay, in the three terms. It's a common factor. So then you can take this common factor out. Okay. And you're leaving with this expression. So this expression equal to 0. Remember, huh, this is you're trying to find the lambda so that this expression equal to 0. Is it possible e to the power lambda equal to 0? Is it possible? No, right? I mean, if lambda is a negative number, it's exponential decay, but it never reached 0, right? Yeah. So this is not possible. So the only way to make this 0 is lambda squared plus a lambda plus b equal to 0. Now that's the only way to make it 0. So this is actually quite an important equation here. So if you look at this equation, it's a second order, right? It's the same order as your original second order linear ODE. And this equation also has coefficient A and B here, which is the same as the coefficient A and B as the original second order ODE, okay? Except you don't have the y prime, y double prime, y prime. You're replaced with lambda square and lambda. So lambda square here is the same order as the highest order of derivative, and lambda here is the order of the first order derivative. Okay, so this equation we call it characteristic equation, because just like the adjective words characteristic, because this equation literally give you back the nature, you know, how the original equation supposed to behave. That give you the feature of the original differential equation. So if you're required to solve this quadratic function, and I think you have all learned in your high school, this is basically a quadratic function. The coefficient here is 1, the coefficient here is a, there's b at here. So you get negative a plus minus a squared minus 4b and divided by 2. You've got two solutions at here. So we're aiming for one solution. Now we end up with actually two solutions. Right? Yeah. So that actually already proved our conjecture, right? Right at the beginning. Is it possible that there's a lambda, exists a lambda such that this is a solution? Which is, the answer is yes. You got 2 at here. However, okay, what's a little bit complicated is this. So if you look at the solution in here, that square root term, the square root term could be, what's complicated? The a squared could be more than 4b, or a squared could be less than 4b, or a squared could be equal to 4b, right? So if a squared is more than 4b, so basically when a squared is more than this 4b here, then you got a number greater than 0. Square root of a number greater than 0, perfect. You use your calculator, you can get it, right? Yeah. Then this, you get a number here, then you got a plus minus. So basically at the end, you get, so there are gonna be what? There are gonna be two distinct real roots or real solutions. That's the first situation. And second situation is, let's say when a squared equal to 4b. So if a squared equal to 4b, then this square root term is gone. Then you can only get a negative a over 2. Okay. So technically, when this happens, it looks like you only get a one solution, right? One solution. But because this is a quadratic term, if you recall, for quadratic term, basically you get, maybe you get a lambda minus 1 square, right, equal to 0. That's what we call, you gotta repeat it. You only get one solution, but we call it it's a repeated real root. Okay, so that number repeated by twice. Okay, so this is 2, and the last one is probably the most a little bit complex one, is that when a squared is less than 4b, then you got a negative number underneath the square root number. And guess what do we have as a solution for lambda? Imaginary, exactly, right? Or in other words, we'll get a complex solution, right? Complex number as a solution. However, you got a plus minus here, right? So basically, for example, let's say if this is less than 0, maybe you got a less than 3, for example, as a square root. Okay. If you got a negative the square root negative 3, which is equivalent to the writing as a j times root 3, right? So basically, you're gonna get maybe a number plus minus j root 3 divided by 2. That's how the solution will look like. So when you have a complex number, and the only difference is plus minus here, and we call that complex, that two complex number, remember what do we call that? You got a number, let's say you got a number 2 plus minus j3, for example. What's the connection between 2 plus j3 and 2 minus j3? It's called, who is it? Conjugate, exactly, right? So these are conjugate. It's a pair of a complex number. It's complex conjugate roots. So that's what we call this situation here. So we get 2 complex conjugate roots. So in the next lecture, that's what we're going to look at for each one individual case, and to present you with the general solution for each one of the cases. Okay. So remember, this is under what umbrella? Huh? Yeah, under the umbrella, this is homogeneous and with constant coefficients. Any questions? Feel free to come over, and I will see you on Wednesday. Well, you can still try specific k times this plus ky times this plus q times this. Obviously, you're not going to be able to find a number satisfying that expression. So they're going to be linear independent. But there are situations that lead to efficient. So for example, if you have a cosine Right? Yeah.
Oh, yeah. Thank you so much.
No problem. Yes. Yeah. Bye bye. Yeah.